Hi, it's Paul Andersen, and this is Science and Engineering Practice 5, Using Mathematics and Computational Thinking. There's no established definition for what mathematics is, but it's essentially an abstract study of quantity, structure, shape, and change. And it's very important in science. What is computation then, and what is computational thinking? Computation is essentially using computers to do calculations for us and a way of thinking about doing science. Because mathematics is important in science, it allows us to represent variables in our studies with actual mathematical variables. In engineering, it's important to improve design. And if you look at the root of any science, you're eventually going to find mathematics. I love this quote from John Louis von Neumann, who's one of the most famous modern-day mathematicians, and he said, "If people do not believe that mathematics is simple, it is only because they do not realize how complicated life is." And what that means is if you're going to study engineering or if you're going to study science, you're going to have to become good at mathematics. It's at the core of everything because science is like an onion. So if we were to look at biology as a science and you were to look at it at just the outer level, biology, you're just going to find biology, things like cells, things like ecosystems. But if you dig a little bit deeper, you'll find that biology is built on biochemistry, these macromolecules, and that in turn is based in chemistry, and chemistry is based in physics, and if we look far enough, at the core, we're going to find mathematics. And so mathematics is really important. It's intimately tied with science. And so let me give you a couple examples of that. One formula that almost everybody's familiar with is E equals mc squared. A lot of people have been looking at this equivalence between mass and energy, but Einstein was the first one to come up with a formula that simply explains how mass can be related to energy and vice versa. And so when we convert, for example, in a nuclear explosion, we're converting a little bit of that mass to a massive amount of energy. Or if we were to look at James Maxwell's study of electromagnetism, so he came up with these equations, Maxwell's equations, which explain electromagnetism, but they also explain optics and electrical circuits. And so you can find these simple core abstract ideas that govern the way science behaves. What is computation then? Computation is doing calculations using a computer. And computers and calculations and math have really revolutionized all of science over the last 50 years. And Seymour Papert, who's one of my heroes, did some early studies on computer programming and how students learn, developed a programming language called Logo. Was the first one to coin this phrase, computational thinking. It's a way that we're using computers to help us model and help us understand the world. Let me give you a concrete example of that. You've maybe seen this demonstration before. The idea is that if we put a bunch of mousetraps around in, let's say, a gymnasium, and we were to balance on each of them one ping pong ball, and then, or let's put two ping pong balls here, and then we were to trigger that, those ping pong balls will fly up into the air and they'll land on other mousetraps, which will trigger more mousetraps. And so you have this what's called a chain reaction going on. Now, if you were to set that up in a gymnasium, you could imagine this is going to take a long time, but we can use simulation software to kind of do that for us. And so this is NetLogo. It's a software program that you can download, and it's an extension of that Seymour Papert's first Logo program. But basically what you do is here you can set up a number of different agents that do different jobs. And so in this one, the red is going to represent one mousetrap that's been triggered, and then these whites are going to represent ping pong balls that fly off. And so when you start it, you can just step through the process one after another. But when you really want to run the simulation, you just click on this Go button up here, and it'll run the simulation really, really quickly. And so you can see a quick simulation of this mousetrap problem. It gives us data over on the side, and we can run it again. You'll find that it doesn't look exactly the same, but it looks very similar. Or we can run it again, and it doesn't look exactly the same, but it has a similar behavior. And so we can get data from that. And so we can use computers to gather a huge amount of data, and they allow us to make better decisions. And so, for example, Mathematica is a computer algebra system that can allow us to model really complex mathematical problems and solve those. And we really live in the age now of big data. In other words, we're getting so much data that we now have to figure out a way that we can deal with that data. Examples could be genomics. These are gene sequencers that are sequencing DNA, and species after species we're figuring out what are the letters within their DNA, and we have to make sense of that. Or connectomics is looking at how the neurons, for example, in our brain are connected together, and there's a huge amount of data. Or meteorology, so it's big data. All this data is being collected, and we have to figure out the science that goes behind that data. And so it's important that our students are able to work with data, and they should be working with data from day one. In engineering, we use computational thinking to do simulations. And so this could be a simulation on the space shuttle and the forces they're put on it, or this would be an actual driving simulator used by the military. And so in engineering, we're using computation to test designs that we have. And so what do we want our students to be able to do? We want them to be able to use mathematics in the science classroom. And that starts with looking at quantities and proper units, and then starting to establish mathematical relationships. We also want them to start doing some computational thinking, and we can do that in two ways. We can have them start building models, and then we can actually run simulations. And so what's a nice progression for that? In other words, in the elementary school, we want them throwing darts at this board. We want them doing mathematics and computational thinking. And we just want to get better and better and better over the years, get closer and closer and closer to that bullseye. And so according to the framework, a good way to start is to actually start them with quantities and units from day one. So the moment that they can count, they should be using rulers and thermometers and protractors to actually be making measurements. And those measurements should have proper units that go along with them. They should also be collecting data as soon as they can and organizing that data into some kind of a chart. As soon as they can, they should be using spreadsheets if that's available. We also want them to look at mathematical relationships, and so we want them to start using words, and then those words eventually become symbols. And so if we're studying motion in a car, for example, we could have them come up with sentences like this: distance equals velocity multiplied by time. So we want them to start by looking at words and explaining what they're seeing or their observations, but we want to transition that to symbols, so math that we can then manipulate and that we can use to refine our theories. When it comes to mathematical modeling, like I mentioned, spreadsheets are really, really important. There's so much data available online right now, and we want kids to start looking through that and becoming comfortable with it. I'm always surprised when they get to my high school class how many students have never ever used Microsoft Excel before or never used a spreadsheet. You might go out and not be a scientist when you graduate high school, but almost everybody is going to use spreadsheets in their job at some point. And so we want our students to start doing that as well. We want to start doing, as they move into middle school and high school, using probes so that we can gather data. This would be a motion sensor or a thermometer hooked up to a computer, so they get this idea that we can gather a huge amount of data, and then we have to go through that. And then don't neglect simulations. Mathematical models or computational models. This again is NetLogo one on climate change, and you can see that they can do things like add clouds, remove or add carbon dioxide, and they can see how that is going to manipulate the environment. Because theories are important, but we want to do experimentation, and computers allow us to do a huge amount of experiments in a short period of time, and it's pretty easy. NetLogo is a great example of one, but there's a lot of other modeling softwares out there. And so again, mathematics and science are really intimately tied together, and we want students to not have a fear of mathematics. We want to show them why mathematics is important, because that's something that science teachers really can do. And I hope that was helpful.